Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to go over another problem of how to use the ideal gas equation to solve a problem. So in this problem here, again, the the way you're going to decide to use the ideal gas equation or not is to see if the problem is indicating some sort of change between or some change of a character of the gas, right? So is the volume changing? Is the amount of the gas changing? Is the temperature changing or anything like that? If something is changing, you're not going to use the ideal gas equation. You're going to use some other equation, some other gas law like Boyle's law or Charles' law, or even the combined gas law or something like that, right? So that's the first thing you want to do. Once you've decided that, hey, nothing's changing, all they're doing is giving me some characteristics of the gas and they're trying to find a, one of the other characteristics of the gas under these set conditions, then you can go ahead and use the ideal gas law or the ideal gas equation to find your answer. Now, in this problem, it's a little bit trickier because here they're not giving you a lot of the information you think you would need. So let's get into this problem here. So they're asking us, what is the density of argon gas in an incandescent light bulb at 80.8 degrees Celsius and 131 kilopascals? So obviously there's no change going on here. They're giving me some conditions of the gas, right? The pressure in kilopascals and the temperature in degrees Celsius. And that's really all they're giving me, and they're asking me to find the density. So this seems like it would be a problem for the ideal gas law. But if we write out the form that we're normally familiar with, right, that would be the PV equals nRT formula, the PIVNERT, as it's sometimes called. It doesn't seem that they're giving us enough information, right? So they're not giving us the volume of the gas. They're not giving us the amount of the gas. So how are we going to be able to find the density? Well, this is where the other form of this ideal gas equation comes in. So the other form takes into consideration that the number of moles is equal to the mass of the gas, right? And we can represent that mass as G for the mass in grams, right? So the mass in grams over divided by the molar mass, right? So whenever you convert from grams to moles, you're multiplying by the conversion factor of the molar mass. But in that case, it's flipped. Moles are on the top, grams are on the bottom, so that grams can cancel out. That's the same as dividing by the molar mass for you algebra nerds out there. So this ends up being the equation. So the number of moles is equal to the mass of your sample divided by the molar mass, right? So what we can do is we can substitute in this for the n, right? So the equation then becomes PV equals, and then I'm going to put G over M. So instead of N, it's going to be G over M for the molar mass multiplied by RT. So this form, we can rewrite it as PV equals GRT over the molar mass. All right, so we have this other form here. Notice that we have mass in grams and we have volume. Now let's go back to density. Density, what are the units of density? The units of density are units of mass over volume. That's what density is. It's mass over volume, right? And we have in our equation mass in grams, G, and we have volume. So all we have to do to get the density is to get the mass over the volume. Let's solve this equation for mass over volume. So we go ahead and manipulate this equation. I want the volume on this side, right? So if I get this on this side, so I'm going to multiply by the molar mass, multiply both sides by the molar mass. So then the molar mass cancels out, right? So I can get rid of the molar mass now. Clean this up. And now I can divide by RT. So if I divide by RT, so now that cancels out. And then I have G left on this side, right? So we can get rid of that now. And then now look, I can divide by the volume. So I divide by the volume on both sides. So the volume cancels out now. So I can get rid of the volume on this side. And now I have mass over volume is equal to this. So finally I can rewrite it this way. So G over V, which this is equal to density, D for density, is equal to now the molar mass multiplied by the pressure divided by RT. So all I need is the molar mass, which I can get because I know we're dealing with argon. I looked that up on the periodic table. So I got the molar mass. Pressure is given to me here in kilopascals. R is a constant that I can look up. And then T is temperature, which I am given here. So I have everything I need. So now all I need to do is plug everything in. And so now there's the other thing. So our R value, what R value do we choose? There's a couple of different, there's 2 or 3 different R values we could use. And the difference in the R values is merely their units. So the normal one, or I shouldn't say normal one, but the one that I'm usually using is 0.082058, and that is liter atmospheres over Kelvin mole, right? But you don't have to use the R value with that in there. You can use the one that has kilopascals in it. So if we use the one with kilopascals, that would be 8.314 and the units there is liters, and instead of atmospheres, it's kilopascals over Kelvin mole. So because I have a different unit, I have a different number because the conversion is involved in that number here. So since they're giving me kilopascals in the problem, it would behoove me to use this one since that lessens or reduces the number of conversions I need to do. So now all I need to do is plug in the molar mass. The molar mass of argon is 39.95 grams per mole. I'm going to multiply that by the pressure, kilopascals, 131 kilopascals. Okay, divided by R. R value is 8.3145 liter kilopascals over Kelvin mole, right? And then finally, temperature. Temperature is 80.8 degrees Celsius. We got to change that to Kelvin. So that's going to be 80.8 degrees Celsius. And we're going to add 273.15. And that gives us, let me calculate that really quick, 354.0. 354.0 Kelvin. So here's 354.0 Kelvin. And I'll put that down here. Let me double check my calculation. 354. Okay, so now I have everything plugged in. So here, moles cancels out with moles on the bottom. Kilopascals on top, cancels out with kilopascals on the bottom. Kelvin cancels out Kelvin here. And then we have what's left. We have grams over liters, which is the units of density, mass over volume. So looks like we did it right. So when we calculate this out, we get 1.78 grams per liter. So let me double check. Yeah. So here, again, for those of you interested in sig figs, notice I have 3 sig figs. That's because according to the rule of multiplication and division, that the answer should have the same number of sig figs as the measurement with the least number of sig figs. So here I have 4, here I have 3, here I have 5, and here I have 4. So 3 is the least number, so I have 3 sig figs for my density. And that, ladies and gentlemen, is how it's done. I hope you enjoyed this video. If you learned something from this video, then please, by all means, like the video, share the video, hit that like button, subscribe to my channel, and then make sure that you hit the notification bell so that way you can be notified by all the videos I put out. But click all, though. Click all. And then finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. And also, if you have a problem or a question you want me to go over or a topic you want me to cover, then please let me know. I would love to do that for you. Thanks for joining me and have a great day.